Have you ever sensed that the universe is hiding something big, something our best theories can't quite pin down one moment? The cosmos looks predictable. The next, it reveals a cold patch in the microwave background that shouldn't exist, or a massive drift pulling galaxies as if pushed by forces we've never identified. Then, there's a star dimming in patterns no known object should produce. And the unresolved question of why matter won the cosmic coin toss against antimatter. These aren't small curiosities. They press against the very structures of physics we depend on. If uncovering these unresolved space mysteries fascinates you, like and subscribe to the video. Now, let's begin. You can learn more about the universe each year. Add new maps, gather more data, and refine the tools used to study the sky. Yet the overall picture can still feel incomplete. Scientists have measured the faint afterglow of the Big Bang, the light called the cosmic microwave background. They have sent telescopes far beyond Earth's orbit and built detectors that can sense small ripples in space-time. They have created models that describe how galaxies form and how gravity shapes large structures. Even with all of that work, something unexpected continues to appear from time to time. A detail that does not match the rest. An observation that sits just outside the lines of what the current rules can explain. There are cold regions in the sky that look slightly out of place. There are stars that change brightness in ways that do not follow any known pattern. There are areas of space that seem more empty than they should be, or more aligned than statistics would normally allow. When these kinds of findings show up, they do not break the field of physics, but they do make researchers slow down and take another look at what they thought was settled. They show that even though science has built strong frameworks, those frameworks are still tested by new data. Some of the tests are small. Some reach across billions of light years. But each one reminds us that large parts of the universe remain unexplained, even when we can measure them directly. These mysteries are not rumors or stories made up to create interest. They come from real instruments, from satellites, observatories, and long-term surveys. They appear in data that has gone through repeated checks. They show up again when different teams use different tools. They stay in the record because they are repeatable and because they matter. They are the kind of signals that make scientists sit together in a quiet room, review the numbers, and admit that something is not lining up the way it should. Some of these oddities might eventually be understood. Others may remain unresolved. Either way, they point to limits in our models. They remind us that the universe does not always follow the paths we expect it to. A clear example of this is a feature in the cosmic microwave background. The oldest light we can observe. When you look at a full map of that light, it resembles soft static. It is made of tiny temperature differences spread across the sky. Differences so small that they are measured in millionths of a degree. These variations trace the seeds that later grew into galaxies and clusters. Most of them follow a random pattern, just as scientists predicted. But there is one region that stands out. It is colder than the rest. Not a small dip, but a noticeable patch, large and clear enough to draw attention every time the map is shown. This feature became known as the cold spot. It was first detected in the early 2000s by a satellite named WMAP, short for the Wilkinson Microwave Anisotropy Probe. Later, the European Planck mission observed the same area with higher resolution and confirmed that the feature was real. The cold spot covers a massive region in the direction of the constellation Eridanus. It spans roughly 1.8 billion light-years across. which is a scale difficult to imagine. It is not cold in the sense of everyday temperature. It is cold relative to the surrounding patterns of the cosmic microwave background. Patterns that are normally very consistent. The challenge comes from the fact that the early universe should have been almost uniform. The small fluctuations we see across the sky fit well into statistical expectations. They match what scientists would expect from natural variations in a young, expanding universe. But the cold spot does not fit. It is too deep and too large. And it does not follow the usual distribution. Because of that, researchers began searching for causes that might affect the light as it traveled to Earth over billions of years. One idea was the supervoid explanation. A supervoid is a region of space with far fewer galaxies than average. Light passing through such an underdense area can lose energy due to a process that links the expansion of space with the gravitational landscape. If the supervoid were large enough, it might make the cold spot appear cooler than it truly is. Observations did find a void in that direction, but the void was not deep enough or wide enough to account for the full effect. It was like seeing a shallow depression when a deep canyon would be required. The numbers simply did not match what was needed. Another idea said that the cold spot could be a rare statistical event, something that appears even in a universe governed by random processes. But calling it a 1 in a million chance does not satisfy most researchers. When a feature at this scale appears in such detailed data, people prefer a physical explanation. That led to a more speculative possibility. Some scientists wondered whether the cold spot could be an imprint from something outside our visible universe. The thought is that if our universe expanded from a bubble of energy, and if other bubbles formed around the same time, then a collision between two bubbles during the early inflation period could leave a mark. That kind of collision might create a large, unusual region, like the cold spot. This idea sits far from everyday physics. It involves the possibility of a multiverse, which is not part of the standard model of cosmology. Yet it shows up in discussions because the cold spot does not cooperate with simpler explanations. The idea is not widely accepted, but it remains one of many attempts to describe a feature that refuses to behave like the rest of the map. For now, the cold spot stays on the list of cosmic mysteries because it is measurable, sharp, and unexplained. A different puzzle began with measurements of motion across large distances. The universe is expanding, and galaxies move apart as space stretches. The farther a galaxy is, the faster it recedes. This pattern has been consistent since Edwin Hubble described it in the 1920s, but some observations from the late 2000s suggested that there might be an additional motion, something not caused by expansion alone, a slow drift involving thousands of galaxy clusters, all moving in the same general direction, a drift that did not fit with known structures. The effect was studied by looking at how photons from the cosmic microwave background scatter when they pass through hot gas around galaxy clusters. This process is known as the kinetic Sunyaev-Zeldovich effect. When researchers analyzed these scattering patterns, they noticed that many clusters seem to share a common motion toward a region near the constellations Centaurus and Hydra. This phenomenon was called dark flow. Galaxies always move under the influence of gravity. Local groups pull on each other. Large structures shape the motion of smaller ones, but dark flow appeared to operate on a scale beyond those local influences. It was not caused by nearby structures like the Great Attractor or the Shapley supercluster. Those factors had already been taken into account. The drift pointed beyond anything visible, as though something large outside our observational reach was influencing the motion of entire clusters. The first response was to check for errors. Teams examined their methods, recalibrated instruments, and tested their assumptions. Some follow-up studies found hints of the same motion, while others did not. The evidence remains mixed, but the original signal was strong enough to be taken seriously. If the motion is real, it suggests that something beyond the observable universe is affecting matter on our side of the cosmic horizon. The observable universe has a limit. We can only see as far as light has traveled since the Big Bang, which is about 46 billion light-years in any direction when accounting for expansion. Beyond that, the light has not reached us yet. If something massive lies outside that boundary, we cannot see it directly, but we might detect its influence on the objects within our view. That is the unsettling possibility raised by dark flow. It implies a structure or mass so large that it pulls on galaxy clusters across hundreds of millions of light-years. Some scientists have suggested that the source of this influence may lie outside the part of the universe we can observe. Others think it could be tied to the overall shape of space-time on scales far larger than anything mapped so far. And there are ideas that move even further from familiar ground, describing how our universe might sit as one bubble among many inside a larger multiverse. In that picture, a much larger neighboring bubble could create a pull strong enough to guide the drift of thousands of galaxy clusters. The idea does not rely on imagination or fictional worlds. It comes from the mathematics that describe how mass bends space-time and how that curvature can extend beyond the limits of what we can see, not in a science fiction sense, but in the literal physics of mass and curvature and pull. There are ideas suggesting that the early universe may have formed structures far larger and heavier than anything that appears in our models today. These would not be normal galaxies or clusters. They would be regions dense enough or empty enough to bend space-time in ways that leave marks across billions of light-years. If they existed, their gravitational pull could stretch across the cosmos and shape motions we only now have the tools to detect. These structures would sit far outside the familiar range of what telescopes can map. Yet their effects could drift into our data. They would not be exotic in a fictional sense, but in a physical one, coming from simple mass, acting over enormous distances. There is also the idea that we may be misreading the measurements. Observing motion on such large scales is complex. The signals are faint, and the ways photons scatter through hot gas around clusters can add noise. Some studies have suggested that the drift we call dark flow could result from distortions caused by structures in our region of the universe. Distortions that we do not yet understand well. If that is the case, then the explanation would be much simpler. It would mean that nothing unusual lies beyond our cosmic horizon, and that the drift is only an artifact of how the data interacts with models. Several newer analyses lean toward this cleaner view and find weaker evidence for a coordinated motion. Even with these ideas, the truth is not clear. Dark flow sits in a space between confirmed measurement and speculation. Different surveys have produced different results. Some teams argue that the signal is too weak to trust. Others continue to investigate, refining models, creating larger simulations, and developing improved ways to examine the subtle interaction between background light and the hot gas in clusters. Their goal is to determine whether the drift is a measurement error or a sign of a force beyond our reach. If it is real, the implication would be significant. It would mean that the universe is not only expanding but being drawn towards something outside our field of view. Something large, something hidden behind the edge of what light has had time to reach. This possibility makes the idea unsettling. The motion would not be about galaxies moving randomly. It would be about why they move in the same direction across long distances. If the answer lies beyond the limit of what any future telescope can see, then it becomes a mystery without a clear resolution. Understanding the motion of galaxies is something science has done well for decades. But explaining a drift that points beyond the visible boundary adds a layer of uncertainty. It highlights how even the largest scale maps leave room for questions we cannot yet answer. Unusual behavior appears even in places much closer to us. Most stars follow patterns that make sense. They shine steadily. If they dim, the drop is small and predictable, often caused by a planet passing in front of them. The dimming repeats on a schedule because planets orbit with regular timing. When a star does not follow these rules, the change stands out. That is what happened with the star known as KIC 8462852, often called Tabby's star. It is named after Tabitha Boyajian, the astronomer who helped bring attention to its strange behavior. The star is about 1,470 light-years away. In a region not known for unusual objects, it is an F-type main sequence star, which means it is slightly hotter and larger than the Sun, and should be stable over long periods. When NASA's Kepler Space Telescope looked at it, the data showed something unexpected. Kepler watches stars for tiny dips in light caused by the transit of planets. These dips are usually small, around 1% for a planet the size of Jupiter. But Tabby's star had dips much larger than that. Sometimes the brightness dropped by 5%, sometimes by 15%. And in one event, it dipped by more than 22%. For something to block that much light, it would have to be enormous. Even if an object large enough existed, the dimming would repeat in a cycle as the object orbited. That was not happening here. The dips came without warning, did not match any known timing, and did not align with any pattern. They were irregular and deep, separated by stretches of normal brightness. Scientists explored the usual explanations. A swarm of comets could cause irregular dimming if they were moving in clusters with large tails of dust and ice. But the number of comets needed would be far beyond anything observed in any star system. A ring of debris from a recent collision might create a similar effect, but it would likely show more consistent structure. Dust clouds could filter light, but they usually affect specific wavelengths more than others, leaving a trace that instruments can detect. None of these matched the full behavior. Along with the short dips, the star appears to be getting dimmer over longer periods, which makes simple explanations even harder to support. A single event cannot explain both the sudden drops and the slow decline. The idea that caught public attention was the possibility of an artificial structure. A few scientists mentioned that the pattern, while unlikely, did not fully rule out a large set of objects built by an advanced civilization. They compared it to the concept of a Dyson swarm, an arrangement of many platforms orbiting a star to capture energy. No one suggested this was the most likely answer. It was offered because the observations did not match any known natural cause. Once the comparison was made, people became curious. The thought of a normal-looking star behaving this strangely made the idea hard to ignore, even though it remained only a cautious possibility. It gained attention because the behavior was so unusual that familiar explanations were not enough. More grounded ideas continued to surface. Some researchers suggested that clouds of interstellar dust, drifting between Earth and the star, could create patterns that change over time if the dust has uneven density. Others proposed that the star itself may have internal processes we do not fully understand, causing its outer layers to shift or clump. Stars can behave in surprising ways when interacting magnetic fields or large convection zones become unstable. But none of these options explains every detail. The dips are too deep, the timing is too irregular, and the long-term dimming adds an extra layer that does not align with standard models. The star's behavior remains puzzling, and the more scientists learn, the more complex the picture becomes. Years of observation have not solved the mystery. Telescopes have monitored the star in multiple wavelengths to see how the light changes over time. Some data sets show that certain wavelengths drop more than others, hinting that dust may play a role. Other data sets show dips that do not match dust behavior. The star keeps dimming in unpredictable ways, and none of the leading theories fit all the facts. It has become a rare case where every common explanation falls short, even though the idea of an artificial structure is no longer taken seriously as the main answer. The fact that it had to be mentioned at all shows how far the star lies outside normal patterns. Tabby's star shows that even places we think we understand still have their surprises. Among thousands of stars that behave exactly as expected, one can stand out simply by refusing to follow known rules. It reminds us that the universe does not always match our models, and that some of the most interesting findings appear when something behaves just slightly wrong. Those small breaks in the pattern often lead to larger questions about how stars form, age, and change. Radio telescopes add another layer to these questions. For decades, scientists have scanned the sky for signals that might show signs of life elsewhere. They have looked for repeating pulses, narrowband tones, or patterns that stand out from natural noise. They have sent out signals as well, including simple codes and detailed messages carried by spacecraft. Yet the sky remains quiet. This silence is strange, because the numbers suggest that life should be common. There are countless stars, many with planets. Some of those planets sit in zones where liquid water can exist. With enough time, life could emerge, and with more time, intelligent life could form as well. This is the core of the Fermi paradox. If life should be widespread, then why is the universe so silent? What makes the silence more striking is its consistency. No repeating signals, no clear messages, no confirmed detection across any survey. But there have been rare moments when a signal stood out. The most famous is known as the WOW signal. Detected in 1977 at Ohio State University's radio telescope, it lasted for 72 seconds and was strong, narrow, and clean. It came from a region of space where nothing should have produced such a signal. The astronomer who saw the printout circled the spike and wrote the word WOW in the margin, giving the event its name. No one has ever explained it. It never repeated. It did not match any known satellite, star, or natural source. It remains one of astronomy's enduring mysteries. Sitting alone in the data with no clear cause, its short duration makes it hard to test, and the lack of a second detection makes it impossible to confirm. It came and went like a voice in a crowd that vanishes before you can turn around. Fast radio bursts add another example of signals from the universe that arrive without warning and leave more questions than answers. These events, often called FRBS, appear as short, sharp pulses of radio waves. Each pulse lasts only a few milliseconds, which is just a few thousandths of a second. The first one was discovered in 2007 when researchers were reviewing older recordings. It was not something anyone expected. The signal was a clean spike buried in data that had already been stored away. When more searches were done, astronomers found additional events scattered across the sky. The intensity of these bursts makes them especially puzzling. In the brief moment when an FRB appears, it can release as much energy as the sun produces over the same period. For something so short to be so powerful, the source must involve extreme conditions. Some bursts come from distant galaxies many billions of light years away. Even after traveling across such long distances, they remain bright enough for radio telescopes on Earth to detect. Some FRB repeat, giving scientists a chance to observe them again. Most do not. A one-time burst, especially one lasting only a few milliseconds, provides almost no information about its origin. Scientists have suggested several natural explanations. One idea involves neutron stars, which are the dense remnants left behind after massive stars collapse. Some neutron stars have magnetic fields far stronger than anything we can produce in a laboratory. These magnetic fields can twist and snap, releasing radio waves in sudden bursts. A type of neutron star, called a magnetar, known for having especially strong magnetic fields, is often considered a likely source. Magnetars can produce bright pulses of energy, and some recorded events match this behavior. But magnetars cannot explain every FRB. Some bursts have shapes and timing that do not match what magnetars typically create. There are also ideas involving black holes. When black holes merge, or when matter falls into them, the surrounding region becomes extremely energetic. Intense magnetic fields could twist in ways that release radio pulses. Another idea suggests that an object orbiting near a strong magnetic source could pass through a region where conditions align to produce a repeating cycle. A 16-day repeating pattern once gained attention because it introduced structure into a phenomenon that usually appears random. A repeating signal is easier to track and measure. But even that pattern has natural explanations that do not require unusual physics. The challenge is that none of the proposed theories explain every type of FRB. Some bursts arrive with multiple peaks. Others arrive with only a single sharp spike. Some repeat once every few days. Others repeat only after months or years. Most never repeat. The wide range of behavior makes it difficult to match them all to a single type of source. There is no long message inside the bursts. There are no patterns that suggest intelligence. The bursts arrive and disappear too quickly, leaving behind only data points on a chart. They show that the universe is full of activity. But that activity does not appear to be aimed at us. This brings up a different kind of mystery, the silence of the universe. For decades, scientists have used radio telescopes to search for signals that might come from advanced life. They have scanned broad ranges of frequencies and looked for anything that stands out from natural sources. They have sent signals of their own, including simple radio messages and spacecraft with detailed information in case another civilization might detect them. But in all that time, nothing clear has come back. The quiet creates a puzzle known as the Fermi paradox. The basic idea is simple. If life is common in the universe, and if intelligent life has the potential to spread or communicate, then why do we not see any signs of it? One answer is that we may not be listening in the right way. Radio waves are easy for us to use, but advanced civilizations might use methods we do not understand. They could use signals outside the range we monitor. They may use light pulses or particles like neutrinos that pass through matter without being absorbed. They may use technology we have not imagined yet. If that is the case, our current search methods might not detect anything. Another possibility is that civilizations choose to remain silent. They may avoid sending signals for safety reasons. If announcing their presence carries risk, quiet becomes a reasonable choice. There is also the idea that advanced life is still extremely rare. The universe is old, but the rise of intelligent species may require precise conditions that do not happen often. If only a few civilizations exist at any moment, the chances of two of them overlapping in time and communicating may be very small. Signals sent long before humans developed technology would pass by unnoticed. Signals sent far in the future might never reach us. It is also possible that life exists in forms that do not build cities, tools, or machines. Life could form under thick layers of ice on distant moons, inside dense atmospheres, or within oceans of gas on giant planets. Such life may never develop technology. It may never produce artificial signals. If that kind of life is common, the silence in the radio sky makes sense. But the silence still feels strange, because the building blocks of life, carbon, water, and energy are found throughout the galaxy. With so many planets and so much time, it seems like more should have happened. What makes the silence even more interesting is that it is not simply a lack of noise. It is a lack of evidence. The more we search, the more we find natural signals from stars, planets, and galaxies, but none that clearly show intelligence. The quiet becomes a kind of message by itself. It tells us that something about the path to advanced life might be rare or difficult, or it tells us that our assumptions about communication may be incomplete. A different mystery appears in the structure of the universe when we look at the cosmic microwave background, the faint glow left over from the Big Bang. Cosmology is built on the idea of isotropy, which means the universe should look almost the same in every direction when viewed on large enough scales. Galaxies spread out evenly, forming patterns that do not favor any particular direction. When scientists mapped the cosmic microwave background using satellites like WMAP and Planck, they expected to see random variations in temperature spread across the sky. For the most part, that expectation held true, but there was an unexpected alignment in the data. Large-scale temperature fluctuations, described as low multipole moments, appeared to point along a particular direction in the sky. Instead of being random, they formed a tilted pattern. This alignment became known as the axis of evil. The name was meant to be humorous, but the issue it describes is serious. If the alignment is real and not a measurement error, it challenges the assumption that the universe has no preferred direction. It suggests that something in the early universe created a directional pattern. This is important because isotropy is a major part of cosmology. If the universe has a preferred direction, then some of the main ideas about how it expanded and evolved may need to be revised. It could mean that inflation, the rapid expansion after the Big Bang, happened in a way different from what models describe. It could mean the universe has a particular shape. Some possibilities include a universe that is not perfectly flat, but slightly curved. Others involve shapes like a torus, which resembles a donut. In such shapes, light can move in ways that create repeating patterns across the sky. Before considering major changes to theory, Scientists checked for simpler explanations. Foreground signals from our own galaxy can interfere with measurements. Dust, gas, and radiation from the Milky Way can overlap with the cosmic microwave background. Instrument settings, scanning patterns, and satellite orientation can also create artificial features. Researchers removed these effects and compared data from different missions. After all, corrections were applied. The alignment weakened, but did not disappear. The patterns still showed up. This leaves open the possibility that the alignment is real. Some scientists think it might be a clue pointing to physics beyond our current models. Others think it might be a coincidence, a rare but possible outcome in a universe so large. Humans are good at seeing patterns, even when none exist. So it is important to test these ideas carefully. But the fact that the alignment appears in multiple datasets suggests it is more than simple randomness. It raises a question that has no clear answer. If the universe has a preferred direction, what is causing it? Another mystery emerges when we simulate how galaxies form. In computer models based on the lambda-cold dark matter framework, dark matter gathers into halos of different sizes. The largest halos host large galaxies like the Milky Way. Around these large halos, smaller halos form, each one capable of gathering gas and forming stars. These small systems become satellite galaxies. In simulations, a galaxy like the Milky Way should have hundreds of these satellites orbiting around it. But actual observations show a different picture. When telescopes such as the Sloan Digital Sky Survey and the Gaia mission map the region around the Milky Way, they find far fewer satellite galaxies. Instead of hundreds, there are only a few dozen. Most of these are small, faint, and difficult to detect. Andromeda, our nearest spiral galaxy, also has far fewer satellites than models predict. This mismatch is known as the missing satellites problem. One explanation is that small halos may not gather enough gas to form stars. Early radiation from the first stars and galaxies may have heated the gas and pushed it out of small halos, leaving them dark and invisible. Another idea suggests that dark matter behaves differently on small scales than the simple cold dark matter model describes. It may spread out more than expected or interact in ways that prevent the formation of dense clumps. These possibilities are being tested, but none solve the problem completely. As more observations came in, surveys like Sloan Digital Sky Survey and Gaia mapped the region around the Milky Way with increasing detail. They revealed new faint systems, some stretched by tidal forces and others barely holding together. Even with these discoveries, the number of satellites remained far below what simulations predicted. Andromeda, our closest spiral neighbor, showed the same kind of mismatch. With far fewer satellites than the model suggested, each new dataset helped fill in small pieces. But the overall pattern stayed the same. The predictions pointed toward hundreds of small galaxies. We were seeing maybe a few dozen. That's a big gap. The mismatch between simulations and observations led to a simple question. If the models say these satellite galaxies should be there, where are they? One explanation suggests that many of the satellites may exist, but are simply too dim for our instruments to detect. A small galaxy can struggle to gather enough gas to form stars. And without enough stars, the system barely produces light. A galaxy made mostly of dark matter, with only a few faint stars, would be almost invisible against the background of the sky. It would still orbit the Milky Way, but it would be difficult to detect. unless our surveys were extremely sensitive. As telescopes improved, researchers began to discover more of these ultra-faint dwarf galaxies. Large surveys like the Sloan Digital Sky Survey and newer programs using more precise instruments started revealing tiny systems scattered around the halo of the Milky Way. Some contained only a few thousand stars, spread thinly in an extended cloud. Others were stretched or distorted by the Milky Way's gravity, making them even harder to study. These discoveries helped increase the satellite count. But even with these new finds, the numbers still fell short of what models predicted. The gap narrowed, but it did not close. Another idea focuses on the early universe. In the first billion years after the Big Bang, intense energy flooded space as the first stars and galaxies formed. This period, called reionization, filled the universe with high-energy radiation. If a small dark matter halo tried to collect gas during this time, that radiation could heat the gas and push it away before it could cool and condense. Without enough gas, these halos would never form stars. They would exist as structures made almost entirely of dark matter, quiet, starless, and invisible. This idea explains why the halos exist in simulations but do not show up as bright star-forming galaxies in the sky. There are also questions about the nature of dark matter itself. The standard model of cosmology uses something called lambda-cold dark matter, a framework where dark matter moves slowly and clumps easily, forming structures across many scales. But if dark matter behaves differently if it is slightly warmer, or if its particles interact in subtle ways, then it might not form small clumps as efficiently. That would change the number of small halos around galaxies like the Milky Way. In that case, the simulations might need to be revised because the assumptions about dark matter would not match reality. Underneath these ideas is a broader concern. If our galaxy does not match the predictions of dark matter simulations at small scales, how reliable are those simulations overall? Much of our understanding of cosmic structure, from the shape of the cosmic web to the formation of large clusters, comes from the same framework. If the model struggles with small objects, does it also have weaknesses at larger scales? Some scientists think this is simply a matter of observation limits. They believe that as surveys become more sensitive, more satellites will be found, and the gap will shrink. Others believe that the mismatch points to a deeper issue, something in the underlying physics that needs to be updated. This is why the missing satellites problem remains active. It is not only about counting tiny galaxies. It reaches into the fundamentals of cosmology. It affects how we understand dark matter, how the first stars formed, how galaxies grew, and how the Milky Way's halo is shaped. The number of known satellites continues to increase, but the full explanation is still out of reach until it is resolved. The problem stands as a reminder that the universe may not be following the exact rules we expect. Black holes add another challenge to our sense of how the universe works. Many black holes are only a few times the mass of the Sun. Some, like the one at the center of the Milky Way, reach a few million solar masses, but there is a category much larger than these ultra-massive black holes. These can reach billions of times the mass of the Sun, making them some of the most extreme objects in existence. They anchor the centers of large galaxies and power bright quasars that can be seen across vast distances. What makes them puzzling is their age. Astronomers have found ultra-massive black holes that existed only 700 million years after the Big Bang. on cosmic timescales. That is extremely early. The universe at that point was young. The first stars were still forming, and galaxies were small and irregular. Yet in this early era, some regions already contained black holes as massive as the cores of modern galaxies. This timing creates a problem. The standard path for forming a large black hole begins with the death of a massive star. After the collapse, the black hole grows slowly, feeding on gas, dust, and nearby stars. It can also grow through mergers with other black holes. But even under ideal conditions, this process takes time. Gas cannot fall in faster than certain limits without being pushed back by radiation pressure. Collisions and mergers also take long periods. A black hole cannot jump from the mass of a star to the mass of a billion suns in only a few 100 million years, at least not under the rules as we currently understand them. To explain this, some scientists propose that the earliest black holes may have formed through direct collapse. Instead of forming from a single star, a huge cloud of primordial gas might have collapsed straight into a black hole. This would skip the stellar stage entirely and start the black hole off with a much larger mass. With a head start, it could reach extremely high masses more quickly. Direct collapse black holes are still theoretical, but they provide one way to bridge the timeline. Another idea is that the early universe was better suited for rapid growth. Gas was denser. Galaxies collided more often, and black holes may have had more material to pull in. If the environment allowed for faster accretion, meaning faster inflow of gas, then early black holes could grow at rates not seen today, even with this advantage. However, the growth required to reach billions of solar masses in such a short time still pushes the limits of current models. There is also the possibility that our understanding of black hole physics needs refinement. The physics of accretion disks, radiation pressure, and feedback mechanisms around black holes is complex. Small differences in how these processes work at high energies could lead to large differences in growth rates. Some researchers have even suggested that dark matter could play a role in feeding early black holes. Though this is still speculative, each idea points to the same issue. The early universe may have had conditions or processes that we do not yet fully understand. These early giant black holes are not rare outliers. Dozens of high redshift quasars, bright sources powered by these massive black holes, have been found. Their light has traveled more than 13 billion years to reach us. They are bright, visible, and well measured. The mystery is not their existence, but their timing. They force scientists to question whether the growth models, the environmental assumptions, or the physics itself may be incomplete. Until these questions are answered, ultramassive black holes remain a sign that something about the early universe does not match our expectations. Another puzzle appears when we look at the expansion of the universe. The expansion is not a theory, it is an observation. Light from distant galaxies is stretched as space grows, shifting toward longer wavelengths in a process called redshift. The farther away a galaxy is, the faster it appears to move. This relationship, first described by Edwin Hubble in the 1920s, leads to a number called the Hubble constant, which describes how quickly the universe expands over large distances. Modern instruments allow scientists to measure this expansion using two main methods. The first method looks at the early universe. It uses the cosmic microwave background, the ancient light from about 380,000 years after the Big Bang. Satellites such as Planck have measured tiny temperature variations in this light with high precision. By applying the standard model of cosmology to this data, researchers can calculate how fast the universe should be expanding today. This approach gives a value of about 67 kilometers per second per megaparsec. A megaparsec is a unit equal to about 3.26 million light-years. The second method focuses on the nearby universe. It uses objects called type Ia supernovae and Cepheid variables, which behave like standard candles. A standard candle has a known brightness. By comparing its true brightness to how bright it appears from Earth, we can calculate its distance. Combining this distance with its redshift gives a measurement of the expansion rate. This method produces a higher value, around 73 kilometers per second per megaparsec. The issue is that both methods seem reliable, yet they do not agree. The early universe method uses well-tested physics and extremely clean data. The nearby universe method is supported by decades of refined observations and careful calibrations. Independent teams have checked and rechecked both approaches. They have reduced uncertainties and corrected for potential errors, but instead of moving toward the same number, the two values remain consistently different. This disagreement has become known as the Hubble tension. Scientists once hoped that better data would close the gap, but the opposite has happened. As measurements become more precise, the difference becomes harder to ignore. Instead of converging, the two estimates drift further apart. This has led some researchers to consider a new question. If both measurements are solid, then perhaps the issue does not lie with the data. Maybe this isn't a measurement problem. Maybe it's a model problem. When scientists consider the Hubble tension carefully, the question naturally shifts toward the model itself. The standard model of cosmology includes dark matter, dark energy, and the inflationary expansion that took place right after the Big Bang. It has been successful in describing many features of the universe. But the disagreement in expansion measurements suggests that something might be missing. One possibility is that the assumptions built into the model are slightly off. The value of dark energy is usually treated as constant, but it may change over time. If the energy pushing the universe apart has evolved, even just a little, it could alter the relationship between the early universe and the one we see today. Another idea suggests that new particles or forces may have been present during the first few 100,000 years of the universe's history. These particles could have influenced expansion and then faded out, leaving no direct trace. Or perhaps gravity behaves differently on the largest scales, in ways that general relativity does not fully describe. These possibilities are still speculative, but they exist because the gap between early and late measurements will not disappear on its own. One proposal receiving attention is known as early dark energy. It suggests a brief surge of energy that appeared before the cosmic microwave background formed. This burst would have slightly increased the expansion rate at that specific time, which would change the predicted value of the Hubble constant today. Even a small change in early dynamics could alter how we interpret the ancient snapshot of the universe. Other ideas involve phantom energy, or interactions between dark matter and dark energy. These interactions might subtly affect how structures form or how fast space expands. What makes this challenge difficult is that both methods of measurement appear valid. The cosmic microwave background gives us a picture from when the universe was an infant just 380,000 years old. Supernovae and Cepheid variables give us information about the universe now. Together, they are like two photographs from opposite ends of a lifetime. When the pictures do not match, something in the middle must have changed. Whatever the answer turns out to be, it will likely teach us something important about the nature of dark energy. the shape of space-time, or the early conditions that set the universe on its path. For now, the tension sits quietly within modern cosmology. It is not dramatic, but it persists. It behaves like a small crack in a foundation, subtle but impossible to ignore. If left unresolved, it could reshape how we understand the universe. As we shift from cosmic expansion to the structures within the universe, another set of mysteries appears. When most people picture a galaxy, they imagine a clean spiral with large arms or a smooth elliptical form. These are the types commonly shown in textbooks because they follow predictable patterns. Spiral galaxies have organized disks. Elliptical galaxies have rounded shapes. Even irregular galaxies often follow patterns shaped by gravity and time. But beyond these familiar categories, astronomers have found galaxies that defy the usual models. Some galaxies form nearly perfect rings. Others show shapes that resemble an X or twist into loops that do not match standard predictions. The deeper we look into space, the more examples we find. They are not rare outliers, but recognized categories with enough members to raise questions. Consider a well-known example called Hoag's object. It is a nearly perfect ring galaxy. A bright circular band of stars surrounding a round core. There are no visible arms. There are no obvious bridge structures. The ring is unusually clean compared to galaxies thought to form through collisions. The standard explanation for ring galaxies involves a smaller galaxy passing through a larger one. The gravitational shock spreads outward like a ripple in water, creating a circular wave of star formation. This can produce ring-shaped structures, especially when the collision is recent or messy. But Hoag's object is different. It does not show the usual debris or distortions that would indicate such an encounter. The symmetry is so precise that it does not fit the expected outcome of a collision. And because no intruder galaxy is visible nearby, astronomers cannot easily point to a cause. Another unusual category includes polar ring galaxies. These systems have a central galaxy with a second ring of stars and gas orbiting at a steep angle, almost like a giant tilted wheel. This configuration requires extremely specific conditions. The merging galaxies must have the right mass, the right orientation, and the right timing for the rings to settle into stable orbits. Yet astronomers have found several galaxies with this arrangement. Their existence suggests either that the required conditions are more common than expected, or that other processes may be at work. Some spiral galaxies also show X-shaped bulges when viewed from the side, instead of a smooth central region. The stars form a shape resembling an X cutting through the core. Many scientists believe this comes from the orbits of stars trapped within a bar structure, a straight feature running through the galaxy's center. As the bar rotates, stars follow elongated paths that create the X pattern. But this explanation has limits. Not all barred galaxies show the shape. The process that causes it remains unclear, and the details of how the orbits align in such a precise way are still being studied. Even more puzzling are the long arcs that appear in deep space images. Some arcs are explained by gravitational lensing. When a massive object, such as a galaxy cluster, sits between us and a distant galaxy, its gravity bends the light, stretching the distant galaxy into curved shapes. But in some cases, the arcs appear too smooth or too isolated to match known lensing patterns. A few show structures that seem duplicated or extended without an obvious lensing object between them and Earth. Alongside these examples, there is an entire category called peculiar galaxies. This label does not describe one shape, but rather anything that does not fit into normal classifications. Some peculiar galaxies have warped disks. Others have off-center cores or star clusters that appear disconnected from the main structure. Many of these features are thought to result from galaxy mergers or close interactions. When galaxies pass near one another, their gravity can pull arms, twist disks, and distort shapes. But because we are observing these galaxies from millions or billions of years in the past, we only see the results, not the event that caused them. Any collision signs may have faded long ago. This creates a challenge. Reconstructing a galaxy's history from a single image is like trying to understand how a structure was built by looking only at the leftover pieces. Simulations help, but they rely on assumptions that may not capture every detail. And with new telescopes revealing more galaxies in greater detail, the variety of shapes continues to grow. Some galaxies lean heavily to one side, even though nothing nearby seems to be pulling them. Others have long, disconnected arms that stretch for great distances before fading away. Tidal streams, long trails of stars created during mergers, sometimes appear too well organized to match predicted patterns. Each new observation adds another piece to a puzzle that the current models do not fully solve. This raises a broader question. Could these unexpected shapes point to missing physics? Dark matter may behave differently in certain environments, or there may be forces or interactions that only become noticeable under specific conditions. While none of these possibilities have been confirmed, the variety of galaxies that break the usual rules suggests that our understanding of galactic evolution is still incomplete. The universe continues to build structures in ways that challenge our expectations. The unusual galaxies are not errors. They exist. They have been photographed and cataloged, and while several theories attempt to explain them, none cover every case. The gap between models and observations remains. Another large-scale mystery involves the motion of our own galaxy. When scientists chart the movement of galaxies near us, they notice that their motion is not random. The expansion of the universe explains why galaxies move away from each other overall. But it does not explain why entire regions drift toward a specific direction. Our own region, which includes the Milky Way, the Virgo cluster, and dozens of galaxy groups, appears to be moving slowly toward a patch of sky. This collective motion is known as a bulk flow, and it does not match simple expansion alone. This movement led to the idea of the Great Attractor. In the 1970s and early 1980s, astronomers studying galaxy velocities noticed a pattern when they corrected for the expansion of the universe. The galaxies were still drifting toward a region between the constellations Centaurus and Norma. The distance was estimated to be about 150 to 250 million light-years away. At first, some scientists suspected measurement errors or incomplete data, but as more observations were collected, the motion persisted. Our local group of galaxies, including the Milky Way, is moving at over 600 kilometers per second toward that direction, and we are not alone. Many neighboring galaxies and clusters show similar motion. This suggests that something with significant mass is pulling on our region of space. But identifying what is causing it has been difficult for one simple reason. We cannot see the area clearly. The part of the sky where the Great Attractor lies is blocked by the dense disk of the Milky Way. Dust and gas obscure the region in what is called the zone of avoidance. Optical telescopes cannot penetrate it well, so astronomers must rely on infrared, radio waves, and X-rays to peer through the obstruction. These methods reveal some structures, including the Norma cluster, the Centaurus cluster, and the Hydra cluster. These are large collections of galaxies with significant mass, but when scientists add up the mass in these regions, it does not fully explain the motion we observe. This is where the mystery deepens. The combined mass of the known clusters does not appear strong enough to pull so many galaxies at such high speeds. The bulk flow remains larger than expected. That means there may be mass we cannot see, or structures we have not yet mapped. Some unseen mass, or some structure we haven't fully mapped, seems to be at play. As astronomers tried to understand the large-scale motion of our region of space, another idea began to take shape: the Great Attractor. With all its influence, might not be the final answer. It could be only a local effect, a single step towards something even more massive farther out. That brought attention to a structure known as the Shapley supercluster, discovered in the 1930s by Harlow Shapley. It is one of the most significant concentrations of galaxies in the nearby universe. The region contains more than 8,000 galaxies, all gravitationally bound, and sits roughly 650 million light-years from Earth. Its mass is enormous, larger than anything found closer to us, and some researchers believe it might be the true cause behind the pull we observe. But even this explanation is not complete. The motion of galaxies does not line up perfectly with the position of the Shapley concentration. The numbers do not fit as neatly as models would predict. This suggests that something else may be influencing the large-scale drift. There may be structures beyond the Shapley supercluster, structures too distant or too faint for us to detect that contribute to the overall pull. These structures could be massive superclusters, dense filaments, or regions of space richer in matter than anything we can currently map. This leads to a deeper question: what lies beyond our cosmic horizon? The cosmic horizon marks the boundary of the observable universe. It is not an edge in the physical sense, but a limit created by the speed of light. Regions farther away exist, but their light has not had time to reach us. Anything beyond that boundary remains invisible. If huge structures exist outside the observable universe, they could influence the motion of galaxies within our view by their gravitational pull. Their presence would not be seen directly, but their effects could still reach across space. This connects to other cosmic puzzles, including the concept known as dark flow. Some scientists have wondered whether the Great Attractor and dark flow are different perspectives of the same phenomenon, motion caused by an enormous structure or set of structures outside the part of the universe we can observe. If so, the source of the pull is not something in the visible sky. Instead, it could be located beyond the horizon, shaping the motion of galaxies through mass alone. Even with these ideas, the picture remains incomplete. There is still no final answer about what is causing the movement. The Great Attractor represents a difficult intersection between what we can measure and what likely exists but remains hidden. The motion is not hypothetical. It is not a mathematical error. It is real. It has been confirmed through repeated observations. Galaxies are drifting, and they are doing so in a consistent direction. The cause of that drift, however, is not fully known. New surveys attempt to map this motion more precisely. Instruments that rely on radio wavelengths can see through the gas and dust in the Milky Way that block optical telescopes. Projects like the Taipan Galaxy Survey and the upcoming Square Kilometer Array aim to gather more complete information. These efforts may reveal structures currently hidden from view or provide better estimates of the mass in nearby regions. For the moment, though, the pull remains a quiet reminder that space is not a static backdrop. Forces shape it, guide it, and influence the paths of galaxies across hundreds of millions of light years. Something large is out there, something we have not yet fully mapped. While large-scale structures like the Great Attractor and the Shapley Supercluster challenge our understanding of cosmic motion, other puzzles appear in regions of space where almost nothing exists. Most of the universe is made of space itself. Galaxies look crowded in telescope images only because the images zoom in on dense regions. In reality, galaxies are separated by enormous distances. They sit like isolated islands in a vast sea of emptiness. But even with that understanding, one region pushes emptiness to an extreme. This region is known as the Boötes Void. It is one of the largest known voids in the observable universe, located in the direction of the Boötes constellation. It spans nearly 330 million light-years across. The scale is difficult to imagine. If the Milky Way were placed at one side of the void, and you traveled at the speed of light, you would still be crossing the empty region hundreds of millions of years later. And for most of that time, you would pass hardly anything at all. When the Boötes Void was discovered in the 1980s, astronomers were surprised. They were mapping galaxies to study how matter is distributed across the universe. They expected gaps, since cosmic structure forms in a web-like pattern with dense regions connected by filaments. But the size of this void was unexpected. Instead of thousands of galaxies in that volume, astronomers found only a few dozen, with perhaps a couple hundred at most. Compared to typical regions of the same size, it was almost deserted. Cosmic voids are common. They form naturally as gravity pulls matter into denser regions, leaving empty spaces in between. But the Boötes Void is unusually large. Its emptiness is sharper than predicted by many simulations. It is not just a gap. It is a gap that exceeds expectations. That raises questions about how it formed. One idea is that the void emerged from the merger of several smaller voids. In this scenario, low-density regions near each other expanded and combined over billions of years, forming a supervoid. This process is possible, but it leads to another question. Why would so many low-density regions form in the same place? And if this can happen once, why do we not see more supervoids of similar size scattered throughout the cosmos? Another explanation says the void may trace back to the early universe if that region started with slightly less matter than average, even by a small percentage. It might have expanded differently, with less matter to slow it down. The space inside the region could grow faster, leaving behind an area with fewer galaxies. But this challenges the idea that the early universe was nearly uniform. If a region began with such a noticeable difference, it would suggest the early cosmos had more variation than standard models predict. Dark energy adds another layer. Dark energy drives the accelerated expansion of the universe. Some scientists think its effects might cause voids to grow more quickly over time. Regions with less matter may expand faster than denser regions, making the emptiness even more pronounced. This remains an active area of research because dark energy itself is still not well understood. Its behavior could influence the growth of large voids, but the details are unclear. There is also a more conceptual angle. Some researchers have suggested that voids, like the Boötes Void, could be used to test alternative cosmological models. These include theories that propose the universe may have a preferred direction, or that expansion might vary from region to region. If voids reflect deeper physical principles. They could help distinguish between competing models. So far, none of these models have gained enough support to overturn current theories, but the Botes void continues to attract attention precisely because it does not match predictions easily. The void has also inspired casual speculation. Some astronomers have joked that if someone wanted to hide something enormous in the universe, the Botes void would be a reasonable place. Anything located deep inside might be nearly impossible to detect because light from that region would take so long to reach us. And so little matter exists there to reflect or emit light. The joke highlights a real scientific point. The sheer emptiness of the void makes it a challenge for observation. Despite its strangeness, the Botes void is important. Studying it helps refine models of galaxy formation and cosmic evolution. If we can understand why it formed and why it is so empty, we can better predict how matter should be arranged on the largest scales. If we cannot explain it, that also carries meaning. It could signal a limitation in our understanding of dark matter, dark energy, or the early conditions of the universe. For now, the Botes void remains one of the clearest examples of how absence can be just as informative as presence. Not all mysteries are made of matter. Some come from regions where matter is missing. And in this case, what we don't see might be the most interesting thing of all. Cosmic dust may sound small, almost unimportant. But in astronomy, it plays a much larger role than most people expect. It fills galaxies, collects in clouds, and shapes the way light travels through space. It absorbs starlight, hides stars from view, and helps gas cool down enough for new stars to form. Dust also aids in the creation of planets by helping solid materials stick together. Without it, many of the structures we see today, spiral arms, dense clouds, clusters, would look very different. Dust is a quiet but essential part of how the universe organizes itself. But there is a puzzle. We are finding too much of it too early. To understand why that matters, it helps to look at where dust comes from. Dust forms from heavy elements: carbon, oxygen, silicon, iron. These are not created in the Big Bang. They form inside stars, especially massive ones. When these stars reach the end of their lives, they explode as supernovae. Those explosions scatter heavy elements into space. Over time, the material cools, collides, and sticks together to form tiny solid grains. Later, those grains gather into clouds and spread through galaxies. This process is slow. It requires generations of stars. First, the stars form. Then they live and fuse elements. Then they die. Only after all of that does dust appear in large amounts. Early in the universe, none of this should have happened yet. In the beginning, the universe contained only hydrogen, helium, and a trace of lithium. Heavier elements had to be forged inside the very first stars, known as population 3 stars. These stars were made from pristine gas and are thought to have been extremely massive and short-lived. Still, even they needed time to build and release enough heavy elements to produce dust. But when telescopes like the Atacama Large Millimeter Array and the James Webb Space Telescope began looking deep into the early universe, they found something unexpected. Very distant galaxies, galaxies less than 1 billion years old, already contain large amounts of dust. In some cases, the dust was thick enough to block significant portions of the galaxy's starlight. That level of chemical maturity does not match the expected timeline. One example is the galaxy named MAX 0416_Y1, located about 13.2 billion light-years from Earth. It existed only 400 to 500 million years after the Big Bang, yet it contains dust similar to what we see in much older galaxies. That means several rounds of star formation and death must have already occurred. But the universe should not have had enough time for that to happen. So astronomers began looking for explanations. One idea is that early stars lived much faster lives. Massive stars burn through their fuel quickly and explode as supernovae within a few million years. If the early universe produced unusually large numbers of these stars, heavy elements could spread more rapidly. That would speed up the creation of dust. But even with this scenario, models still cannot fully explain the volume of dust observed in some early galaxies. Another possibility involves black holes and quasars. Young galaxies often contain energetic black holes that eject powerful winds. These winds can compress gas, spark new star formation, and help distribute heavy elements. This could accelerate the buildup of dust. But not every dust-rich galaxy shows signs of an active quasar. So this explanation does not work in all cases. Some researchers have suggested more exotic sources of dust, such as pair, instability, supernovae. These hypothetical explosions come from extremely massive stars much larger than any seen today. They could produce enormous amounts of heavy elements in one event, but these stars remain theoretical. No direct evidence confirms they existed. Another challenge is that dust is fragile. Shock waves from supernovae can destroy grains almost as fast as they form. Radiation in the early universe was more intense than it is today. Galactic environments were also more chaotic. Dust in this era should have been easily broken apart. So not only do we need a mechanism to create dust early, but we also need a way for it to survive. The tension grows as more observations come in. Astronomers measure dust through its effect on light, especially in infrared wavelengths. These measurements clearly show dust where our models say there should be very little. And the more we observe, the more dusty early galaxies we find. Some are bright in infrared light, meaning they are actively forming stars through thick layers of dust. Others are faint or invisible in certain wavelengths because dust blocks their light almost completely. All of this hints that the early universe may have been more active than expected. Perhaps the first galaxies formed stars extremely quickly, burning through gas and enriching their surroundings much faster than our models predict. Or maybe our understanding of dust formation is incomplete. We may be missing key steps about how dust grains grow or how they survive harsh conditions. Whatever the case, dust appearing this early remains one of the universe's quieter puzzles. The dust should not be there according to standard timelines, but it is. That mismatch pushes scientists to look again at the details of early star formation, galaxy growth, and chemical evolution. Until that mismatch is resolved, it stays on the list of mysteries that challenge our assumptions. Another puzzle comes from an unexpected place: quasars. When we think about the structure of the universe on the largest scales, one principle often stands out: uniformity. Not perfect uniformity, but statistical uniformity. Galaxies gather into clusters, filaments, and huge walls of matter. Voids lie between them. But zoom out far enough, and the universe should look the same in every direction. No preferred orientation, no special alignments. But quasar data is showing something that breaks this expectation. Quasars are extremely bright sources powered by supermassive black holes at the centers of galaxies. As matter falls into these black holes, it heats up and produces jets of radiation. These jets point in specific directions, following the rotation axis of the black hole. Because of this, astronomers can measure the orientation of a quasar by studying the polarization of its light. In the early 2000s, several research groups began noticing patterns. When they looked at the orientations of quasars spread across huge regions of the sky, they saw alignments, not random orientations, but similar ones. The spin axes of quasars were pointing in roughly the same direction, even when those quasars were billions of light years apart. The regions where this occurred were larger than any known cosmic structure, spanning 4 to 5 billion light years. This was unexpected. Nothing should be able to coordinate objects across that distance. Gravity does not work on that scale in a directional way. No known physical process links the spin of black holes, separated by billions of light years. So astronomers examined the data carefully. They checked for measurement errors. They tested for interference from dust within our own galaxy. They looked for bias in the sample of quasars, but the alignments still appeared in repeated observations, gathered with different instruments and in different parts of the sky. If the alignments are real, then the next question is what could cause them? One idea is that the large-scale structure of the universe might be more organized than we thought. Perhaps vast filaments or flows of matter extend even farther than current models suggest. If galaxies formed along these enormous structures, their spins might align over time. That would imply the cosmic web is more influential than our simulations show. Another possibility involves the early universe. During the inflationary period, an extremely brief moment when space expanded faster than the speed of light, certain directional imprints might have been set into the fabric of space. These imprints could still exist today and influence the orientation of distant quasars. There is also the question of cosmic topology, the shape of space itself. If the universe is curved or twisted on very large scales, that geometry could guide the orientation of galaxies and black holes over billions of years. This is still speculative, but it is one of the areas researchers explore when observational data does not match expectations. There is also the unknown, a possibility that the alignments reflect something we have not yet considered, something in the early universe that left a structural mark, something in dark matter or dark energy that affects spin on huge scales, something about the fabric of space that we do not yet understand. Whatever the cause, these quasar alignments challenge a core assumption that the universe is homogeneous and isotropic at large scales. If that principle breaks down, even slightly, it could require changes to our cosmological models. It might shift how we understand the formation of galaxies, the shape of the universe, or the physics of the earliest moments. For now, there is no agreement. The data remains. The explanations remain incomplete. And the fact that objects separated by billions of light years appear to share a common orientation shows just how many pieces of the universe still lie outside our understanding. Each new survey adds more detail, but the pattern persists, and the presence of that pattern, stretching across the largest distances we can observe, tells us how much remains untouched by our current theories. It tells us just how little we truly understand about the largest canvas there is. The idea that matter fills the universe seems obvious to us today. We see stars, planets, gas, dust, and everything built from atoms. But according to the rules of physics, this outcome should never have happened. When the universe began, in the first 10 to the power of minus 36 seconds, temperatures rose above 10 to the power of 27 Kelvin. At those conditions, the universe was a hot, dense mix where particles and antiparticles formed and vanished in perfect balance. For every proton, there should have been an antiproton. For every electron, there should have been a positron. The laws that govern these particles do not show any strong preference. They treat matter and antimatter almost the same. And yet, when we look around, nearly everything we see is made of matter. Antimatter is almost completely absent. It does not fill galaxies. It does not form stars. It does not combine into stable structures. This is not a small detail. It is one of the largest inconsistencies in physics, because when matter meets antimatter, they annihilate each other. They leave behind only energy. If the early universe had contained equal amounts of both, the result would have been complete destruction. No atoms, no stars, no galaxies, just leftover radiation drifting through space. But that is not the universe we live in. Something happened. Somehow matter survived, and antimatter did not. This puzzle is known as the baryon asymmetry problem. It asks a simple but deep question: why does anything exist at all? One idea is that the early universe created a tiny imbalance, maybe for every billion particle-antiparticle pairs. There was one extra matter particle. When the pairs annihilated, that small remainder would be enough to form everything we see today. Every star, every planet, every living thing. But where did that 1 in a billion advantage come from? Some theories point to CP violation. CP stands for charge and parity. Charge refers to the electrical nature of a particle. Parity refers to how physical processes behave when viewed like a mirror image. In theory, if you flip a process in a mirror and switch matter for antimatter, the outcome should look the same. But in certain rare decays, such as those involving mesons, this symmetry is slightly broken. These small differences have been observed in particle accelerators. However, the amount of CP violation found so far is far too small to explain the massive imbalance we see in the universe. Other ideas look to cosmic inflation. During that brief moment after the Big Bang, the universe expanded faster than the speed of light. Some researchers think the conditions during inflation may have baked a preference for matter into the fabric of space itself. There are also proposals involving unknown particles or forces that existed only in the earliest moments before fading away. These ideas connect to grand unified theories and supersymmetry, but none have been confirmed. Another suggestion is more speculative. Perhaps some regions of the universe contain mostly antimatter, while our region contains mostly matter. But if this were true, the boundaries between these regions should glow with gamma-ray signals caused by annihilation. We do not see them. Every observation so far shows that the observable universe is overwhelmingly matter-based. Scientists continue searching for clues. High-energy experiments at CERN look for rare particle interactions that might reveal new types of CP violation. Cosmologists examine the cosmic microwave background for subtle signs of early asymmetry. But the mystery remains. This is not a puzzle about distant galaxies or strange black holes. It is about the very existence of everything. Matter should not have won, but it did, and something gave it that advantage. Questions about the earliest universe lead naturally to another mystery. one that challenges our understanding of emptiness itself. When we imagine empty space, we think of nothing. A perfect vacuum, no dust, no atoms, no sound, just silence. But quantum physics tells a very different story. According to quantum field theory, every point in space contains fields, electromagnetic fields, gravitational fields, strong and weak nuclear fields. These fields never fully shut off, even in a region with no real particles. The fields still fluctuate. These fluctuations create short-lived particles called virtual particles. They appear for a moment, then vanish. Allowed by the uncertainty principle, they are not imaginary. They have measurable effects. One example is the Casimir effect. When two metal plates are placed extremely close together in a vacuum, so close that only certain wavelengths can exist between them, the plates experience a tiny force that pushes them together. This force does not come from magnetism or gravity. It comes from the difference in quantum fluctuations inside and outside the gap. The Casimir effect has been measured in laboratories with high precision. Another example is the Lamb shift. When scientists measured the energy levels of electrons in hydrogen atoms, they found small shifts that did not match older models. These shifts are caused by interactions between the electrons and the quantum vacuum. Again, this is not speculative. It is observed and measured. But these examples lead to a massive problem. When physicists try to calculate the total energy in the quantum vacuum, the predicted number is enormous. According to quantum theory, the vacuum should contain an energy density 10 to the power of 120 times greater than what we observe in the real universe. This is the largest mismatch between theory and measurement in any field of science. The problem is known as the vacuum catastrophe. If the vacuum truly held that much energy, the universe would behave nothing like what we see today. Space would curve violently. Expansion would be uncontrolled. Structures like galaxies and stars could not form. But observations show the opposite. The vacuum appears almost empty. The expansion rate of the universe is modest, not extreme. This mystery connects to dark energy, the unknown force driving the accelerated expansion of the universe. Some physicists believe dark energy is simply vacuum energy, but much smaller than expected. Others believe dark energy is something else entirely. Either way, the question remains, why is there so little vacuum energy in practice when theory says there should be so much? Is our math wrong? Is some unknown mechanism canceling almost all of it out? Is the vacuum hiding something deeper? Some speculative models even suggest that quantum fluctuations could create new universes under the right conditions. In these models, a quantum vacuum is not the absence of reality, but a background that can spawn entire space-time bubbles. Even if our universe someday ends, the vacuum might continue producing new ones. And this leads to a philosophical question. If empty space is never truly empty, does nothing actually exist in physics? Or is emptiness just a lower energy state of something more complex? We do not know. But empty space, something people usually ignore, is turning out to be one of the most active, confusing, and important ingredients in the universe. It challenges our idea of what nothing means and forces us to rethink the foundation of physics. Even when we return to more familiar ground, the chemistry of the early universe, we find puzzles. Right after the Big Bang, conditions were perfect for nuclear reactions. For the first few minutes, temperatures and densities were high enough for atomic nuclei to form. This period is known as Big Bang nucleosynthesis. The predictions from this theory are extremely precise. The early universe should have produced about 75% hydrogen, 25% helium, and small traces of deuterium, helium-3, and lithium-7. Observations of hydrogen and helium match those predictions. Measurements in ancient stars and interstellar gas clouds line up almost perfectly with the theory. This agreement is one of the strongest pieces of evidence supporting our current models of the early universe. But lithium does not cooperate. From Big Bang nucleosynthesis, we expect a specific amount of lithium-7, not a large amount, but enough to be detected in the oldest stars. Population: 2 stars that formed early, before most stellar processes could alter their chemical makeup. These stars act like fossils of the early universe. They preserve the original chemical ratios, but when astronomers measure lithium-7 in those stars, they find only about 1/3 of the predicted amount. This gap is not small. In cosmology, predictions match observations down to decimal places. A factor of 3 is huge. That might not sound like a huge gap, but in cosmology, where predictions are accurate down to decimal points, that's a major discrepancy. The mismatch between predicted lithium levels and what we actually observe has earned a name of its own: the cosmological lithium problem. And it is not something that can be dismissed as a simple mistake in measurement. Astronomers have checked the numbers again and again, for decades, using different instruments, different stars, and different methods. The result is always the same. The lithium levels in the oldest stars are consistently too low. This gap tells us that something in our understanding of the early universe is missing or incomplete. One possibility is that the lithium was destroyed inside stars over time. Even the oldest stars may not be as untouched as we assumed. Lithium burns at a lower temperature than many other elements. So if the material inside a star circulates more deeply than models predict, lithium could be pulled into hotter layers and destroyed. This idea is reasonable because lithium is fragile, but the models that describe how stars mix their interiors suggest that the depletion would not be strong enough to erase 2/3 of the expected amount. It could explain a small part of the gap, but not the whole thing. Another idea focuses on the nuclear reaction rates used in Big Bang nucleosynthesis calculations. These calculations depend on how quickly certain isotopes fuse or decay. If one of those rates is slightly off, the predicted lithium production would change. But nuclear physicists have studied these reactions in laboratories for years. Changing the numbers far enough to explain the missing lithium would interfere with the predictions for deuterium and helium. Those predictions currently match observations extremely well. Fixing lithium that way would create new problems in other areas. This has led some researchers to look beyond standard physics. One idea is that exotic particles, such as axions or decaying dark matter, may have existed in the early universe and subtly changed the conditions under which elements formed. These particles could have altered nuclear pathways or changed the temperature of the early universe in a way that affected lithium formation. This kind of hypothesis is exciting, but there is still no direct evidence for such particles. They remain theoretical ideas waiting for support. Then there is a more radical suggestion. Maybe our picture of the early universe needs adjustment. Perhaps the early universe was not as uniform as we assume. Maybe small pockets with slightly different densities or temperatures formed separate chemical histories, creating regions where lithium formed less efficiently. If that were true, it would mean that the early universe had more variation than our standard model allows. It would also mean that the oldest stars we observe might not represent the entire cosmic picture. Only the part we can see, for now. The lithium discrepancy remains. It does not break the standard model entirely. It does not overturn everything we know, but it stands out just enough to keep physicists uneasy. In science, small mismatches matter. They often point to something deeper. They remind us that the universe still holds details that escape our current equations. While researchers continue investigating the lithium puzzle, another mystery appears in an entirely different corner of physics. This time, the puzzle is not about a rare isotope or an ancient star. It is about a number 1 that shows up everywhere. A number with no units, no scale, and no clear explanation. The fine structure constant is a dimensionless ratio that describes the strength of the electromagnetic force between charged particles. Its value is roughly 1/137. This constant, usually written as alpha, influences how atoms hold together, how electrons orbit nuclei, and how light interacts with matter. It appears in quantum electrodynamics, atomic structure, and particle physics. It is used everywhere. Yet no one knows why it has the value it does. Arnold Sommerfeld introduced the idea in 1916 while modifying Niels Bohr's early atomic model to include relativistic effects. The constant helped explain the fine details in hydrogen's spectral lines. What began as a correction became one of the most important numbers in modern physics. Physicist Richard Feynman once described it as a magic number, something that appears without explanation, shaping the universe in a way we do not fully understand. The fine structure constant is powerful because even tiny changes to its value would reshape the universe. If alpha were slightly larger, electrons would be pulled more tightly toward nuclei. Atoms might become unstable. Chemistry as we know it would not exist. If alpha were smaller, electrons would be more loosely bound. Complex atoms might not form. The structures necessary for stars, planets, and life might never appear. The universe works because this constant has the value it does. But why that value, no current theory provides the answer. Some physicists have tried connecting alpha to other constants such as the speed of light, Planck's constant, or the charge of the electron. None of these attempts have led to a complete explanation. It remains a number built into nature with no deeper reasoning we can identify. Even more surprising, some studies using light from distant quasars suggest that alpha may not be constant after all. These observations hint at extremely small variations across space or time. The idea is controversial, and the data is not firmly settled. But if the fine structure constant changes even slightly across the universe, it would mean that the laws of physics may not be identical everywhere. It would also open the door to new physics unknown fields, hidden dimensions, or variations in the structure of space-time. This leads to a broader question. Why does the universe appear so finely tuned? Many constants, the mass of the electron, the strength of gravity, the charge of the proton sit within narrow ranges that allow stars to form and atoms to stay together. If any of these values shifted even a little, the universe could become unrecognizable or even unable to support complex structures. Some scientists think this fine-tuning is coincidence. Others believe it reflects the anthropic principle we observe these values, because only in a universe with these values could observers exist. Still others think there must be deeper laws waiting to be discovered, laws that would reveal why these numbers fall where they do. The fine structure constant sits at the center of that conversation. It is more than a number. It is a sign of how much we still do not know. The fact that this constant appears everywhere, from particle experiments to the light streaming across your room, and yet we cannot explain it, makes it one of the universe's quiet but persistent mysteries. And mysteries do not stop there. For decades, the idea of dark matter has shaped our understanding of galaxies. Dark matter is supposed to be the invisible mass that surrounds galaxies and holds them together. It acts like scaffolding, creating deep gravitational wells that allow stars and gas to gather. Without dark matter, galaxies should not form. The stars inside them should drift away over time. That idea has been supported by many observations, from galaxy rotation curves to gravitational lensing. But then, astronomers discovered galaxies that do not seem to follow this rule. The first major example appeared in 2018, a faint, ghostly galaxy called NGC 5252-DF2. It sits about 65 million light-years from Earth. Observations showed it had stars and clusters, just like many other small galaxies. But when astronomers calculated its mass, something did not add up. The visible matter, the stars and gas, accounted for nearly all of the mass. There was hardly any room left for dark matter. This was shocking. In most galaxies, dark matter outweighs visible matter by at least a factor of 10. But in DF2, the numbers pointed toward almost no dark matter at all. Follow-up observations used different methods to double-check. The results were the same. Then another galaxy appeared with the same issue, NGC 1052-DF4. Two galaxies with little or no dark matter suggested something more than a one-time anomaly. Researchers began searching for explanations. One idea is that these galaxies were stripped during a collision with a larger galaxy. If a strong tidal interaction occurred, dark matter might have been removed, leaving behind only the visible stars. But simulations show that during such collisions, stars and gas are usually stripped before dark matter is removed. It is difficult to separate the visible components from the dark matter in a way that leaves a galaxy intact. Another idea is that these galaxies formed without much dark matter to begin with. Maybe they started from gas clouds that collapsed on their own. But that idea clashes with everything we understand about structure formation. According to the standard cosmic model, dark matter played a crucial role in the early universe. It created the gravitational seeds that allowed galaxies to grow. Without those seeds, the gas should have remained too spread out to form stars. These dark matter-poor galaxies raise an uncomfortable possibility. Perhaps our understanding of how galaxies form is incomplete. Or perhaps the distribution of dark matter is more varied than we assumed. The findings do not erase the need for dark matter entirely. Most galaxies still show strong evidence for it. But these outliers reveal that nature may be more flexible than our models predict. Dark matter isn't just optional. It's been considered necessary to get galaxies in the first place. There is another possibility to consider, one that sits uncomfortably between measurement and theory. It may be that something about the way we detect dark matter is not as straightforward as we assume. Most of the time, astronomers infer dark matter by measuring how fast stars are moving around a galaxy. If the stars orbit too quickly for the visible mass to hold them in place, there must be additional unseen mass at work. That mass is assumed to be dark matter. But in galaxies like DF2 and DF4, the stars are moving slowly. Their speeds match the gravitational pull expected from the visible matter alone. On the surface, that suggests the dark matter is missing. But it could also indicate that the motion of stars in extremely low-density environments follows rules we do not completely understand. This leads into deeper and more radical ideas. Some scientists believe these galaxies might point toward limits in our current model of gravity. According to this view, gravity may behave differently in regions with extremely low acceleration, such as the faint outer zones of diffuse galaxies. This idea is part of a framework known as modified Newtonian dynamics, or MOND, instead of dark matter. MOND changes the laws of motion on very large scales. While many physicists still support the dark matter explanation, galaxies like DF2 and DF4 keep MOND in the broader discussion. They do not prove it, but they show that gravity might have subtleties we have not fully mapped, no matter which explanation turns out to be correct. These galaxies cannot be ignored. They exist. Their motions have been measured, and their properties do not fit neatly into the dominant model. That does not mean the entire model is wrong. It does mean that something is missing, or that the model needs some adjustment at the edges. These galaxies could be rare outliers formed under special conditions, or they could be signs of a deeper oversight in how we think the universe holds itself together. There is a twist to this story. At the same time, researchers are finding galaxies with little or no dark matter. They are also discovering galaxies that appear to be made almost entirely of it. These galaxies contain very few stars. They are faint, dim, and difficult to observe. Yet their gravitational pull suggests large amounts of unseen mass. On one end of the spectrum, we find galaxies with not enough dark matter. On the other end, we find galaxies with too much, and in between lies a theory stretched in every direction by discoveries that do not follow the rules. This contrast is part of what makes the dark matter mystery so compelling. It is not only about the mass of galaxies or how fast stars move. It is tied to how galaxies form, how gravity works, and whether our view of cosmic structure is complete. These dark matter-poor galaxies are like cracks in a wall. Some are small, some are faint, some may eventually be explained, but if enough of them appear, the whole structure may need to be examined from the foundation up. From there, the questions shift to something even more fundamental. Out of everything we observe, time feels like the most straightforward. Time appears to flow in one direction. 1 second follows another. Yesterday passes behind us, and tomorrow waits ahead. We assume time moves at a steady pace. The same for everyone, everywhere. But the closer physicists look at the universe, the less certain that assumption becomes. Some researchers now think time may not be a basic ingredient of reality at all. Instead, it may be something that emerges from deeper processes. Much like temperature emerges from the motion of particles, the signs have been building for a long time. For one, time does not behave the same way everywhere. According to Einstein's theory of relativity, time slows down near massive objects such as stars or black holes. It also slows down for anything that moves close to the speed of light. These effects have been tested with great precision. Atomic clocks, flown on airplanes, placed on mountains, and sent into orbit tick at different rates. In daily life, the difference is too small to notice. But across large distances or extreme conditions, time bends and stretches. It is not fixed or absolute. Quantum physics adds another complication. At the smallest scales, the laws of nature are time-symmetric. They do not care whether time moves forward or backward. If someone filmed a microscopic quantum process and then played the film in reverse, the mathematics would still work. This is very different from our everyday experience. Eggs break, but never unbreak. Smoke spreads, but never gathers back. Memories point only to the past, not the future. So where does the arrow of time come from? Why does it feel like time moves forward, even though the fundamental laws do not require it to? The most common answer is entropy. In thermodynamics, entropy measures disorder, and systems tend to evolve from low entropy to high entropy. A cold object warms to match its surroundings. A deck of cards gets mixed, not unmixed. This increase in disorder gives rise to the arrow of time we experience. It is not that time itself moves forward. It is that entropy increases, and we move along with that trend. But this explanation depends on one major assumption: the universe must have started in a low entropy state. Why it began that way remains an open question. No one fully understands why the early universe had such a special, ordered beginning. Other questions push even deeper. Did time have a beginning at all? If the universe began with the Big Bang, then time may have begun at that moment. But it is also possible that the Big Bang was not truly the beginning. Some theories propose a bounce, a transition, or a cycle. If that is the case, time could extend further backward than we can observe. And if time loops or stretches in ways we do not yet understand, our current model may be only a fragment of a larger picture. Some physicists propose something more surprising. In certain theories of quantum gravity, time does not appear in the basic equations. Time shows up only when enough particles interact in specific ways. In this view, time emerges from relationships within a system rather than existing on its own. A single particle does not have a temperature. Millions of particles do. Time, according to this idea, may be similar, something that appears only when many parts of a system behave collectively. There is also a view called the block universe. According to this idea, the past, present, and future all exist at once. Time does not flow. It does not move. The entire timeline is laid out like a complete landscape. Our feeling of moving from moment to moment is something our minds create as we experience one slice at a time. In this model, every moment that ever happened and ever will happen is already part of the fabric of space-time. Not everyone accepts this. Many scientists argue that time is real and fundamental, and that we simply lack a full understanding of how it works. Others believe time is emergent, tied to the behavior of matter, the increase of entropy, or even the biology of the brain. But across all of these viewpoints, one thing is clear: time is far more complicated than it seems. It shapes every observation, every event, and every life. Yet it may be built on assumptions that do not hold in every part of the universe. The mystery of time does not come with dramatic visuals or distant objects glowing in telescopes. It works quietly under everything. It touches motion, causality, and change. If time behaves differently than we expect or emerges from deeper processes, then our understanding of cause and effect may need to be rewritten on the largest scales. The study of time may turn out to be one of the most important challenges in modern physics. We often think the universe is something we have mostly figured out. We have named the particles, mapped the galaxies, and built models that explain almost everything we see. But then the questions start piling up. a cold region in the cosmic microwave background that defies statistics, a star that dims in a pattern we cannot explain, black holes that grew too fast too early, galaxies with no dark matter, and others made almost entirely of it, signals that appear but have no clear source, constants that shape the universe but have no known origin, patterns in the background radiation that seem to break the rules of symmetry. For every answer we find, another detail refuses to fit. And maybe that is the point. The universe does not explain itself on our schedule. It does not smooth out its puzzles just because we want clean equations. But the fact that we can ask these questions at all, that we can measure a supervoid, or notice the tilt of a quasar, or wonder why antimatter vanished, says something important. It shows that we are still learning. We are still uncovering pieces of a picture that is larger than anything we can yet describe. The closer we look, the more the truth seems to shift. Not because it changes, but because our understanding grows. And maybe, just maybe, the unknown is the most honest part of the whole.